In this clip, we will look into the analysis of Petri nets that have an infinite reachability graph. Remember that we have many runtime properties that we want to analyze on a marked Petri net, such as reachability, boundedness, deadlocks, dead and live transitions, and home markings. Each of these properties requires the analysis of the reachability graph of the Petri net. But how do you do this if the reachability graph is infinite, like the Petri net on this slide? Hence, in this clip I will focus on the question, what if the net is unbounded? To work with unboundedness, we first need to introduce infinity and how we can deal with infinity. So, step 1, calculations with infinity. As a first step, let me introduce a new number. So we have a new number. And I call it omega. And omega is not a natural number. To start working with omega, we need some calculation rules. So let's introduce a few rules. So we have calculation rules. And the first rule is that suppose I have a natural number, then this natural number is always strictly smaller than omega. And suppose I have a number k, which is a natural number, and I add it to omega, then this just equals omega. And similarly, if I have this natural number k, and I subtract it from omega, that just yields omega. So these are the calculation rules. If any natural number is strictly smaller than omega, and adding or subtracting a natural number from omega results omega. So that means we have a new tool in our toolbox. As a next step, we're going to look to markings again. And one way of looking into marking is to look into what is it if a marking is bigger. So the next step is we're going to look to covers. So a marking, let's say M, is strictly covered by some other marking M prime if the following conditions hold. So, first of all, if I take any place, then the marking M should be smaller or equal to M prime for the same place P. And in addition, and that makes it strictly smaller, I also require that there exists some other place, let's call it R, such that the number of tokens in R is strictly smaller than the number of tokens in M prime for R. So that means, and that's why we say it strictly, there should exist a place for which it is really smaller. Now consider the net on the left. So consider our net on the left. If I start with the reachability graph, then I start in a marking where there is a token in place P and one token in place S. And in this marking, I can fire transition T. Firing transition T yields the marking S, Q, B. And in this marking, transition U can fire. So transition U, that brings me to the marking PS and B. And maybe you already notice that I have here PS, which is the initial marking over here, plus some extra. And this is a little bit extra, that is B. So let's go back to the Petri net firing rule. So observe the Petri net firing rule. So suppose I have some marking M, and M is strictly covered by M prime, and transition T is enabled in marking M. So if you recall the firing rule, then the firing rule says that for all places P in P, if we take the weight function and we consider the input place P of transition T, then this number in the weight function should be smaller or equal than the number of tokens in marking M. And this should hold for any place P. But now notice that marking M is covered by marking M prime. Hence, M prime of P is smaller than or equal to the number of tokens in MP. In other words, the conclusions that we can draw: transition T is also enabled in marking M prime. In other words, if a marking covers another marking, then any transition that is enabled in the marking it covers is also enabled in the covering itself. So, if we go back to the strictly covers, and we see what happens here in the firing rule, where we have places P and S one token and B one token, which was strictly covered by this PS. And so we have this covering over there. Then this place B is the one that is strictly covered. The other two are equal to, but this B is strictly covered. So that means that I can introduce an omega for this B, because we know the transition T is again enabled in B. Hence I know I can fire transition T again. So if I do this, I get a firing transition T and a transition firing U, and I know that the resultant marking will be PS2B. And I can continue this. So that means that this B is unbounded. We see this with the transitions T and U that can fire infinitely often. So now what we do is, and that is the big rule for the coverability graph, we introduce omega if a marking strictly covers a marking on that path. A marking on its path from the initial marking. So in other words, if we have for this place R, that if we in the marking MR, and this M prime R is strictly smaller, so MR is there, and the value we find in M prime R, then we introduce R with omega. So that means in this one, because this B is covered, I say I fire it with U, and it gives me the marking with 1P, 1S, and omega B. So every time when there's a place that is strictly covered, then I can introduce omega. So let's apply that on the net on the left. So as for the reachability graph, I first create a table. And I say I have transitions with a preset and a post set. I have transitions T, U, Y, and Z. Transition T has a preset P and has post sets Q and B. Transition U has its preset place Q and has post set place P. Transition Y consumes from places B and S and produces in place R, and Z consumes from R and produces in S. The initial marking is one token in place P and one token in S. And I will omit the brackets for the remainder of this talk. So, as before, I will create a breadth first search to discover all the markings that I will reach. But I will also directly draw the graph. So that way I can directly see when to introduce an omega. So I start in the initial marking PS. In PS, transition T is enabled. And it brings me to the marking S, Q, and one token in B. So I can draw this in my graph as well. So I have PS as the initial, and I can fire transition T. That brings me to the marking S, Q, B. And don't forget that it is the initial marking. Now I'm in SQB. In it, transition U can fire. That gives me P, S, and B. And transition Y can fire. And it gives me the marking QR. So, if I'm in SQB and I walk back, then I see that the initial marking is PS. Hence the marking PSB strictly covers the initial marking PS. So that means I have PS plus B. Hence I write as PS omega B. So I draw this directly. I can do a U. And now I'm in the marking PS omega B. And I could also fire Y. And it brings me to the place Q, to the state QR. So SQB is now done. And I move to PS omega B. So transition T is enabled. And it results in a marking S, Q, omega B. And I can also fire transition Y. Firing transition Y gives me the marking PR omega B. So in PS omega B I can do a transition T. That gives me SQ omega B. And I can fire a Y. That gives me PR omega B. So PS omega B is done. Now I'm at QR. In QR, transition U can fire, and it gives me marking RP. Transition Z can also fire, and it gives me marking QS. So in QR, I can fire transition Z to go to QS, and I can fire transition U to go to RP. Then we have done that one as well. Now the next one on my list is SQ omega B. And in SQ omega B, transition U can fire. That gives me the marking PS omega B. And transition Y can fire. And that gives me marking QR omega B. And I directly draw them again. So SQ omega B with a U gives me PS omega B. That's this existing state over there. And QR omega B does not exist yet. So let's add it, QR omega B. And I'll fire transition Y to get there. Now the next one on my list is PR omega B. So PR omega B. Transition T is enabled in it, so I can fire it, and that results in marking QR omega B. And transition Z can also fire from PR omega B, and that results in the marking PS omega B. So let's draw. I'm in PR omega B. I can do a U to PS omega B. So that's back to here with a U. And I can do a Y to QR omega B. That's this one. Sorry, I can do a T. This is a T. And this is a Z. Okay, then what's done? Now we're in RP. So RP, that's again a normal marking. And I can fire transition T. Firing transition T leads to the marking RQB. But if I look to RP and to the resulting marking RQB, then actually that is just one marking before it plus a B. Hence, I can rewrite this as RQ omega B. So that is this arrow with a T. And I can do a Z. And that gives me marking PS, which is the initial marking. And it was with Z. Now I'm in QS. In QS, there's only one transition enabled, namely transition U. And firing it leads to the state PS. So that's this one with a U. And we did this one. PS omega B we already did. That's this one over here. QR omega B we did not yet do, so QR omega B. Transition U is enabled in this marking. That results in RP omega B. And transition Z is enabled. This gives me marking QS omega B. So QR omega B is here. I can fire U to PR omega B. That's over here. It was with a U. And to SQ omega B, that is over here with a Z. Then we did this one, we did this one. QR omega B I just did. PS omega B is again over there. We did it. RQ omega B is this one, so we already did it. PS was the initial marking, we did it. PS is the initial marking. RP omega B we already covered over here. And QS omega B we already covered over there. So that means that this is the coverability graph of the net. And as you can see, it is a finite graph, while there's infinite behavior. So what happened? Now, if we look, for example, to the paths where we take transition T and we fire transition U, and we fire transition Y and Z and Y and Z. So we have transitions T, U, and then a Y, a Z, a Y, and a Z. Then we see that this is a trace that is possible in the coverability graph, but not in the PetriNet itself, because T gives one token in place B, I fire transition U, Y removes one transition or one place or one token from place B, Z does nothing with place B, so place B has 0 tokens at the moment, and then transition Y fires again, and I remove again a token from place B, so it gets a negative number of tokens. So this is possible in our coverability graph, but not in our reachability graph. And it is very easy to see that we have the reachability graph and that it is strongly simulated by this coverability graph. To summarize, in this clip we have seen how you can construct a coverability graph to analyze a PetriNet in case the reachability graph becomes infinite. Remember that you can only introduce an omega in a marking M if it strictly covers a marking that is on a path between the initial marking and the current marking M. This means that a coverability graph is a finite approximation of the reachability graph. And if the net is bounded, then the reachability graph and the coverability graph are the same. Also important to realize is that the coverability graph is not unique. So, if you didn't introduce the omega directly, because before, for example, you didn't notice it, that doesn't mean your coverability graph is wrong. It only means that you get a different coverability graph. It only might be slightly bigger. Another aspect is that if you visited the markings in a different order, you could introduce omegas at a different moment. And hence, this also results in a different coverability graph. So, this means that the coverability graph does not exist, only a coverability graph. That brings us to the main property of coverability graphs, and that is that the reachability graph is strongly simulated by any of its coverability graphs. Thus, any behavior the reachability graph has, the coverability graph has. This is a nice, simple and elegant proof. So to see whether you understand strong simulation, I really encourage you to prove this yourself. The consequence of this strong simulation is that if some behavior did not occur in the coverability graph, it cannot happen in the reachability graph. So, if a transition is dead in the coverability graph, it is also dead in the reachability graph. And another property we often use is that if a place is bounded in a coverability graph, it is bounded in the reachability graph. And if it is unbounded in the coverability graph, it is also unbounded in the reachability graph. So that means that you can use the coverability graph to deduce the bound of each place in the net. So the coverability graph is a powerful analysis tool. However, it also requires practice to master the technique. Good luck modeling!